One thing we'd like to be able to do is, given a function f of x, we'd like to be able to determine the maximum and the minimum values that the function attains. Now there's two different types of values, and these are called extreme values or extrema. There's absolute extrema and relative extrema. That's not what we're going to cover in this video. Instead, we're going to cover one key definition that will be used in that video. You notice just an intuitive notion of maxes and mins, high points and low points. Just with our intuitive notion, we can roughly see where these places would be. I can highlight them on the graph. These places seem to be the high places or low places. And again, there's some details I'm leaving out here. Again, we're not going very formal as far as defining relative extrema or what have you. But just looking intuitively at this graph, high points and low points, and even this last graph here, this seems to be a low point. Now, if you look at each of these yellow points that I've highlighted here, there seems to be something unique about all of them. And that's the fact that either the derivative is 0, you see we have horizontal tangent lines at these places, or with this kind of strange last example, the derivative is not 0, the derivative does not exist. Not that the point's not defined, that the point is definitely defined, but the derivative does not exist at that particular point. So because this is where the high points and low points will typically reside, we give these points a special name. We say that x equals c is a critical point. That's our word for this video, the critical point of the function if two things happen. Number one, your point is actually in the domain of f. It's not does not exist because it's not even defined on the original function like an asymptote or something like that, but it has to be in the domain of the original function. And number two, the derivative either equals 0 at that point or it does not exist. Now, the majority of the time it'll be this type where the derivative is 0, but there are certainly cases where you can have a critical point where the derivative does not exist. So let's just run down a couple of simple examples, and hopefully this will help us understand critical points a little bit better. Here's a cubic function. I'm not really quite sure of its graph right this second, but we don't need its graph. We can differentiate it, and we'll take f prime of x, and we get 3x squared minus 6, and we'll set this equal to 0 because that's where the derivative is equal to 0. Now, I don't know where those are yet, so I actually have to solve this equation. This is almost like a question. Where is the derivative equal to 0, or what x's would make f prime be 0? So we have a little algebra. 3x squared equals 6. So x squared equals 6 over 3 is 2. So x equals plus or minus the square root of 2. These guys right here would be called critical points. Now we should also look for any places where this would have a derivative that's undefined. Now for polynomials, if your derivative is simply a polynomial, then you'll never have division by 0 because there's no fractions. You'll never have a negative under a square root because there's no square roots. You'll never have a negative inside a logarithm or anything like that. So polynomials are usually very nice. You never run into any issues. So the only type of critical values, or critical points rather, that functions, polynomial functions would have would be where the derivative equals 0, period. So now one thing that this doesn't tell me is I don't know if these are maxes or mins, and again we haven't got into those details yet. For this video we're just trying to practice finding the critical points. Now here's the graph of this cubic function right here. I went ahead and graphed it, and we can tell just by looking at the graph that right here and right here it seems like we would have horizontal tangent lines. Well, it turns out that these x values is 1.414. That's the square root of 2. And the other one on the left hand side is negative 1.414. That's negative root 2. So we were able to locate these critical values without the need of graphing or anything like that. Now in a later video we'll look at how do you take a critical point like this and define it as a maximum or a minimum so easily without requiring looking at a graph. Because right now all we know is that the derivative is 0. We don't know if it's a high point or a low point, but we'll look at that another time. All right, here's another one, sine x. Now I know the graph of sine has high points and low points on its graph. So I'll take the derivative of sine, we get cosine x. Cosine x's derivative, with the cosine function is never a does not exist value. It's never an undefined value. So the only types of critical points I would get for the sine function, again, are where the cosine function is 0. So I'm going to ask this question, when is cosine 0? Now I know my unit circle pretty well, so I know that cosine is 0 at pi over 2 and 3 pi over 2 and 5 pi over 2, etc. So if we wrote those out in a list, you'd have pi over 2, comma, 3 pi over 2, comma, 5 pi over 2, etc. Now we typically don't like to leave our answer just written out in list form like this. A more appropriate way of saying this infinitely many x values is to say x equals pi over 2. That gives you 1. But then notice, to get all the others, all you're simply doing is adding pi and then adding pi again and adding pi radians again and again and again. You basically just keep hopping back and forth. So we'll say pi over 2 plus k pi. So that's any multiple of pi. Pi over 2 plus k pi, where k is any integer. Now you can either say that in English, where k is any integer, or I'll just use some math symbols here. The bold letter Z stands for the integers, and this little symbol here that looks like a kind of a bent arrow almost means that k is included in the set of integers. So that's a little new math notation for you there. So this would be the set of all your critical points for the sine function there. We get lots and lots of them. All right, now I want to do one last example here real quickly, just to highlight a very subtle little point here. Somebody who's looking at this function, they would say, okay, I'm going to look for my critical values. Instead of doing the quotient rule, I would write this as x to the minus 1, simply so that I don't have to do the quotient rule, and instead I would do the power rule, and we would get -1, -1 comes down, x to the -2, so -1, and instead of x to the -2, I'll write over x squared. So now somebody will look at that derivative and probably say, oh, well I have a critical point at, they look at this guy and say, well, it's never 0 because the numerator is never 0, but it is undefined at 0. At x equals 0. So maybe we have one here, maybe at a critical point at x equals 0. It turns out we actually don't. Now this is a little tricky. Think about why this would be the case. Why do we not have a critical point at 0? Because it certainly does make the derivative undefined. The derivative does not exist at x equals 0. Here's the answer. The original function was not defined at 0. So if you have a value that's not even in the domain of the original function, you can't call it a critical value. Now the absolute value graph, that's totally fine. The derivative, if you think about this one real quick, there's other graphs that have cusps, but we'll look at the absolute value function just real quickly. Here at 0, the derivative at 0 does not exist. But we would call this one a critical value. Why? Well, because the absolute value graph is defined at 0, unlike 1 over x. I'm sure we all know the graph of 1 over x. It kind of looks like this. You actually have an asymptote at x equals 0. So it's not a critical point or a critical value because the original function wasn't defined there.